Okay, welcome to EGR 445. And in the last class, we talked about the design of spur gears in detail. So we talked about the design process. We talked about the concepts in spur gear. We looked at the important dimensions and proportions of the spur gear. And I gave you a step-by-step recipe for spur gear design. Now in today's class, what I'm going to do is I'm going to work out a spur gear problem from start to end. And again, the recipe that we discussed in last class, we will follow the same recipe step by step, but I will talk about the variations that are possible in a gear design. For gear design, we are going to use the data book or the data that is available in the textbook. So please, if you have textbooks, either in hard copy format or in electronic format, please open those because I would be referring to particular tables. And unless you are confident on what table to look at, where to get appropriate data, it might be a little difficult. So at this point, it would be a good idea to open the textbook. So I'm going to start with a very simple problem. So this problem, so we are going to design a spur gear. And in this spur gear, the design requirement is the center distance is 500 millimeters. So there is a specification on the center distance. So let's start with the design problem. So some reason my PowerPoint is not working. I don't know why. Bear with me for a second. Finally. Okay. Design a spur gear. Center distance is equal to 500 millimeters. Input RPM 900, compressor RPM, which is the output RPM, (200) are the torque to be transmitted, (5,000 Newton meter), starting torque, (25% more). So for this problem, find module and width. Assume it to be a 20 degrees stub gear. Second, find number of teeth, pitch circle diameter, and the last but not least is design shaft. In this particular problem, they have not mentioned anything about the material. It's perfectly fine for the gear to be made up with different material than pinion, but in that case, you have to see whether the gear is weaker or the pinion is weaker. If gear and pinion, both of them are made up with the same material, then the pinion is always going to be weaker. So just to minimize our work, I'm going to assume gear and pinion made with same material. And the reason for that is thus pinion is weaker and we will design pinion. So the next thing is torque is equal to, if you look at the torque that is to be transmitted, which is the steady state torque, it's 5,000 Newton meter, but the starting torque is 25% more. So the actual torque that we are going to design the gear for is 1.2 times 5,000, which is 6250 Newton meter. Now this is the gear, and then this is the pinion. Now another design requirement that is talked about is the input RPM is 900 and the compressor RPM is 200. So clearly what that means is this pinion is the input that is rotating at 900 RPM. Gear is the output and the speed is 200 RPM. Now, since the speed values are given to us, the gear ratio is 900 divided by 200, which is 4.5. Now, what that means is the radius of the gear and the radius of the pinion. Radius of the gear divided by the radius of the pinion is equal to 4.5. That is required to maintain this gear ratio. Now, since it's a design problem, it could be specified in different fashion. Sometimes they will give you the center distance, sometimes they will not give you the center distance, sometimes they will give you some additional constraints. So there are some variations in each problem, and depending upon how the problem is set up, we may have to revise this process. But if you look at this particular problem, one thing that is given to us is the center distance between two gears is 500 millimeters. Now, as you can see, the center distance is nothing but radius of the gear plus radius of the pinion. So I have 500 is equal to radius of the gear plus radius of the pinion. And also I have this ratio. And this ratio comes from the gear ratio because the RPMs, the speed of the input shaft and the speed of the output shaft are given. So I can say that RG is 4.5 RP plus RP. This is going to be 5.5 RP, and that gives me diameter of the pinion, which is 182 millimeters, and diameter of the gear is 820 millimeters. So I have found out the value of the diameter of the pinion and the diameter of the gear. Now, please understand, these diameters are purely defined or found out based on the geometry point of view. So basically, the center distance is 500. The ratio of the radii or the ratio of the diameter is 4.5. We got two equations, and we got two unknowns, so we can actually solve this problem. The next thing is, what we want to do is we want to find out pitch line velocity. Vp is equal to pitch line velocity. And pitch line velocity is pi Pn divided by 60. And this, again, whether you consider, so if you look at the gear or the pinion, this is point P and this is Vp. So this point P is shared by the gear and the pinion. So whenever you have this point P that is shared by the gear and pinion, it will have the same velocity, whether you consider that on the gear or whether you consider that on the pinion. So what that means, yeah.
So regarding to the output and input, so is there any case like the input is going to be the gear and the output going to be the pinion?
Output is, yeah, that is possible. So for an example, in this case, what we are trying to do is, if you look at the whole thing, the speed is reduced. The input speed is 900 and the output speed is 200. So that's how the problem is stated. But imagine a case wherein you want the output speed to be more than the input speed, then clearly your pinion and gear will be reversed. But it again depends upon what the requirement is. So for an example, in this particular problem, the application seems to be like you have an electric motor, and that electric motor is attached to a compressor, and the compressor, for compressor to run, is going to require large torque, and that large torque will be supplied by the electric motor. And what's going to happen? The power supplied by the electric motor is going to be the same as the power absorbed by the compressor.
So if you want to increase the output, should we consider the gear as an input?
So if you want to increase the speed for the output, then you would actually have the gear on the input side and the pinion on the output side. But so downfall to that is, if you look at, again, the energy can neither be created nor be destroyed. So you have this equation, T1 omega 1 is equal to T2 omega 2. So if your T1 goes up, your omega 1 has to go down. If your T2 is going down, then your omega 2 has to go up. Because at the end of the day, this power equation is valid. You are not creating energy. It's all just part of the energy conservation. Okay, so moving on to the next part, we have to find out the pitch line velocity. And why do we need this pitch line velocity? Because recognize that we need to find out the velocity factor in the process. To find the velocity factor, we need to find out the pitch line velocity. So this is given as pi, and I'm going to use the gear. So this becomes 8.6 meters per second. Now please note V is less than equal to 12.5. That means CV, the velocity factor. And I would look at the equation for the velocity factor that is given in chapter 28, which is 3 divided by 3 plus V, which is 3 plus 8.6 is equal to 0.26. Now the issue here is what type of material we can choose, and you have a choice. So you can use either the alloy steel, or you can use the regular steel. Whatever steel you want to choose, you can actually just have to find out the appropriate values for the values of sigma. So what I'm going to do is I'm going to find out. So I'm going to assuming alloy steel, sigma value is, I'm going to assume 140 Newton per millimeter square. And since the gear and pinion are made up with the same material, the pinion is weaker. So I'm going to find out the Lewis's form factor. But before I go with determination of form factor, I need to find out like how many number of teeth I should select. The profile is 20-degree stub. So 20-degree stub. For 20-degree stub, to minimize interference, I'm gonna use minimum number of teeth. So T minimum should be greater than equal to 14. So I'm gonna say, let's use number of teeth on pinion is equal to 18. So 18 is the number of teeth on pinion. Now with that, what I know is I can find out the value of Lewis's form factor. And for that, you have to use the equation which is given in the textbook or in the design data book. So you will substitute 175 minus 0.841 divided by 18. Now, a word of caution. So at this point, let's look at the very important equation. Diameter of the pinion is number of pinion teeth multiplied by the module. And this is the most important equation in determination of dimensions. In this particular problem, the twist is the center distance is specified. So in this particular problem, the diameter of the pinion is already known. So diameter of pinion is already known. So number of teeth on pinion that we selected. So basically, this is what we selected. Since we know the diameter, since we know the number of teeth, from this equation, we can easily find out the module. So with that, we know the value of module, but we do not know if the gear that we are designing is capable of supporting the torque that is needed or supporting the tangential forces that are acting on the gear. So here, the design process needs to be slightly changed, and I will make this a note. So note. In this problem, center distance is given. Minimum number of teeth can be found out. Thus, module can be determined. But here is the question. Is this gear or is this pinion safe to transmit power or WT required. So we have to answer this question. So let's start. And if you look at the recipe, we will have to modify this recipe slightly just to make sure that we can solve this problem. So step one is I'm going to find out the tangential force, which is T starting divided by the radius. Now, starting torque is 5,000 times 1.25 divided by 0.182 divided by 2. So this gives me the value of WT. Next part is sigma is equal to sigma naught divided by velocity factor. Sigma naught is 140 and the velocity factor is 0.26. So this is what we got. Now, I just want to write this equation that we are going to use. So WT is equal to sigma multiplied by B multiplied by pi multiplied by M multiplied by Y. And what I want to do is at this point, I want to kind of give you some interesting ideas here. Let's first write down what we know. 5,000, 1.25 divided by 0.182 divided by 2 is equal to sigma is 140 0.26 multiplied by the value of B multiplied by the value of pi multiplied by the value of M, and please note M is equal to 0.182 multiplied by 1000 because it needs to be in millimeters divided by 18. So 1182 divided by 18 multiplied by the value of Y. Can someone tell me what is the value of Y here? Just solve this equation. 0.175 minus 0.841 divided by 18.
0.128.
0.128. So 0.128. So if you look at this in the entire equation, the only unknown is B. So from here, I can find out the value of B. But there is something that you want to be super duper careful about is, yeah, let's just find out the value of B and tell me how much the value of B is. 400. Now, the next thing is what we want to do is we want to look at the module. How much is module? Now, here is the problem. If you look at the B by M ratio, B by M ratio for this particular design is 482 divided by 10.1, which is about 50. What that means is, I just want to give you sort of an idea. 482 is about half a meter gear. That is a disproportionate gear. The B by M ratio for the gears, for the spur gears, could go anywhere between 8 to 10, all the way to 12. So clearly, this proportion is not an acceptable design. So as you can see, it's not acceptable. Acceptable design. So what do we do with this? Clearly, at this stage, assuming that our B dimension is 482 and our module is 10.1, we will have to reiterate the design.
So we can inside.
So yeah, no. So yeah. So now there are a lot of choices here because it's an open-ended problem. Now I want you to think about this problem and tell me what is the path of least work, which means what can I do here? So this is the question. What can I do here that will bring my B down within the acceptable proportions? Yeah.
Change the material.
Yeah, the easiest thing to do here is change the material. Now, if I want to change the material, what would be the best way to change the material? So clearly, we have to iterate the design. Second iteration of design. In the second iteration of design, WT is equal to sigma naught multiplied by CV multiplied by B multiplied by pi multiplied by M multiplied by Y. So what I'm going to do is, now I'm going to substitute all these values that I have. I'm going to assume B by M ratio is equal to, say, 12. And then I'm going to substitute 5,000 divided by 0.812 by 2 182. CV 0.26. So B by M is 12. So I can just write here 12 times M M is 10.1. Multiplied by Y is 0.182. And from here, I should be able to get the value of sigma naught. And yeah,
Why did we square it?
oh, because this became B is equal to 12 times M. So 12 got here and M got multiplied with it. And select the material. That can meet this particular requirement. Are you with me so far? Now, this is not a complete design problem in a sense that if you want to continue with the design, this is not a complete design problem, but if you want to continue with the design, next step is find dynamic load which is WD, which is WT plus WI. Then find static strength, which is WS, and we need to make sure that WD is less than WS. Then find wear load, and we need to make sure WD, WW and WD is less than WW. So these are the steps that we need to finish to complete the design. But if you read this particular problem, this is not asking us to check for the wear load or the static load. What it is saying is, first find the module and find the width, find the number of teeth, find the pitch circle diameter, and last but not least is design the shafts. So what I would do is I would perform these steps in the next problem, but for this problem, I will go ahead and design the shafts. So if you want to design the shafts, first and foremost, we have to decide the configuration. And there are different configurations possible. So you can have a pinion shaft, you can have the gear shaft, something like this. You can have, so this is config 1. You can have the pinion shaft, you can have the gear shaft, this is the config 2. Or you can have, this is config 2. Or you can have config 3. Or clearly you can have a config 4. So you can have cantilevered, cantilevered. You can have simply supported, simply supported. You can have a cantilevered, and you can have a simply supported. Now, what is the advantage of each configuration? So the advantage of each configuration is something like, if you look at the cantilevered, if you want to construct the housing is going to be something like this. There will be a bearing here. 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 Then here, there are going to be seals. Here, there are going to be seals. And then clearly, depending upon the configuration, that shaft could be extended. So this is sort of a compact design, but please try to understand the amount of forces and the moments that are going to come on the bearing, because this cantilever is only supported on the left hand side. So the amount of forces and amount of moments are going to be significant. Now, if you look at this second configuration, then you're going to have something like this. Again, you're going to have bearings here. So in this case, that since the shaft is supported on both sides, the amount of loading that is going to come on the shaft will be less. So it basically will reduce the size of the bearing. But clearly, as you can see, you need the shaft to be extended on either side. And because of the simply supported configuration, the shaft size would be less. But again, the housing side is going to be big. Then you can have this cantilevered. And this basically, which means the pinion shaft will be of bigger diameter. The gear shaft would be of smaller diameter. The bearings designs would be slightly different. And again, there is no right or wrong answer here. You can choose the appropriate configuration that you want to work with and then kind of go from the dimensions. So you can go for the appropriate dimensions and then find out the values of the bending moment, finding out the values of torque, and so on and so forth. So what I'm going to do is I'm going to select, I'm going to assume this configuration. And then I'm going to assume that there is this housing. So this is shaft 1. This is shaft 2. Now, please understand, it's not required that shaft 1 and shaft 2 would be of the same sizes. Depending upon where the bearings are located, depending upon the amount of torque that is applied, depending upon the type of material, the shaft dimensions could be different. So when they ask you to design the shafts, you can design any of these shafts. Either you can design shaft 1 or shaft 2. But if you want to design the gearbox, which means there will be a problem wherein what you want to do is you want to design not only the gear, but you want to design the gear shaft and gear box. In that case, you want to design shaft 1 and you want to design the shaft 2. So I'm just going to assume one shaft design. And here is a technique. The challenge here is the dimensions are not known, but let's try to come up with some approximate dimensions. This dimension is the width B. This B is 12 times M. M is about 10 and 10.1. So this is about 125 millimeters. So width of the gear is 125 millimeters. So what I'm going to do is I'm going to assume that the center distance from the bearing, I'm going to assume the center distance from the bearing all the way to the midsection of the gear is 150. This dimension is clearly assumed. And the reason for that is I just want to make sure that we have enough space to attach the bearing. We have enough space to attach the shaft, the housing, and all other required components. So one thing, TP, which is torque on the pinion, and TG, torque on gear, are different. So when you are designing, so use appropriate torque for design. So for example, if you are going to design the gear shaft, then use the torque on the gear. When you are designing the pinion shaft, use the shaft on the pinion. Just a second, let me connect my power supply. So first and foremost, let's find out the value of WT that we know 5,000, 1.25 divided by 0.182 by 2. Wn is equal to Wt divided by cosine 20, because we are using 20-degree stub, and Wr is equal to Wn times sine 20. So once we find out these values, next step, and we are designing the shaft for the pinion, we have Wr, Wt, and we have Wn. So we are going to find out the maximum values of the moments and the torque. So moment, because of the radial load, is Wr multiplied by 150. Moment, because of the tangential load, is Wt multiplied by 150. Resultant moment is square root of mWr square plus mWt square. We know the value of torque on the gear. The torque is equal to 5,000 multiplied by 1.25 is 6250 Newton meter. So we can find out the value of TEQ, which is square root of mr square plus t square, and assuming steel shaft, tau is equal to 60 Newton per millimeter square. TEQ J tau divided by R, so 60 TEQ so here the diameter will be in millimeter. So if you have calculators, please quickly tell me these values.
Should we change the one meters to 1 meter?
So it depends your W, this one.
Yes.
So you can do either ways. So the only important part here is tau is in 16 Newton per millimeter square, which means this T equivalent must be in Newton millimeter. That means this,
What about the moment?
yeah, so a moment WR, if it is given in newtons, if this is given in newtons, then here it's gonna give you in Newton millimeter, because it's 150 is in millimeters. The only problem here is, if you look at this torque, this is in Newton meter, so this needs to be multiplied by 10 to the power 3. And then there might be something interesting. You will see that sometimes the gear shaft is bigger than the diameter of the gear. I just hope that this doesn't happen in this case. I want you to try this and let me know that that's not indeed the case. Any answers? So only thing I want to caution you here is, it may not happen all the time, but sometimes if you have the gear that is designing way too much of torque, then what could happen is the shaft that you design would be as big as the gear. So this is the diameter of the gear or diameter of the pinion. And then you see that the shaft diameter that you calculate is bigger than the pitch circle diameter of the gear. And that clearly should not be happening. So if something like this happens, what is the best way to solve this problem? Is change the material. So we are assuming the steel shaft. you can change this steel shaft to maybe an alloy steel shaft. And then find new diameter. So design is the process of iteration. And so even if you don't get the correct answer in the very first go, you will have to repeat the calculations, uh, use correct assumptions, and modify the design so it can actually be constructed, or you can actually purchase those catalog items and have that design materialize. So next part, I just want to briefly talk about, and one of your quiz problems is asking you to do this, is like the housing design. How would you design a housing? Now, what is the purpose of the housing? So,
To 96.
so the diameter of the shaft is 96 millimeters. And the pitch circle diameter is 182. So this is good. Everyone okay with me so far? So this case is not happening. So diameter of the shaft for 60 Newton per millimeter square is 96 millimeter. The diameter of the gear or the pinion is 182 millimeters. So that's good. That's okay. Now the next part which I want to talk about briefly before I work out a full problem is design of housing. So how would you design a housing? So housing design. So typically, housing has multiple purposes. First and foremost, the housing covers the design, or the covers, it actually acts like a cover on the gear design. It also circulates the lubrication or oil. That oil lubricates the gears, cools down the gear, and extends the life of the gear. The housing also holds the bearing in place. So many a times the bearing, they need to be preloaded. So when you have the housing and the shaft and you add an interference fit between the bearings, the housing actually is used to preload the bearings. So how would you design the housing? Housing is designed based on most of the geometry considerations. Uh, so if you have a particular shape that housing needs to be, so that it can fit into the machine, or it can fit into that automobile, or if it can fit into the confined space that you have, that would dictate the way the housing looks. So the way to design housing is first draw the gears, then you have already designed the shafts, draw the shafts, and then estimate sort of where the bearing would be located, where the bearing will be located, where the bearing will be located. So clearly here we are not designing the bearing. So we are just going to estimate like what would be the size, approximate size of the bearing. And then we would construct or draw the housing around the bearing. So it would go something like this. Then what you would have is you would have the thickness, then you're going to have the seal, and here usually you would have oil. And the way that gear is going to work is that oil would continuously be splashed and circulated. So whatever is the power loss that is converted into heat, that heat will be transmitted to the housing, and that heat will be dissipated from the housing. Gears typically are about, depending upon how old the gear train is, 80 to 95% efficient. So assuming 90% efficiency, power loss is equal to 0.1 times the power transmitted. And this power that is transmitted gets converted to heat. And this heat needs to be dissipated by housing. So this is Q. So Q is equal to area of housing multiplied by the heat transfer coefficient multiplied by rise in the temperature. This is area of housing heat transfer coefficient and change in temperature. And many a times the free convection, so housing heats up, and what happens is the air that is surrounding the housing would dissipate the heat. So many a times free convection is sufficient. Many a times free convection is sufficient. But if the free convection is not sufficient, sometimes on these gearboxes, you would notice that there will be a fan that is attached to the output shaft. And the purpose of this fan is to increase the airflow that improves the heat transfer coefficient, and that is used in cooling the housing. But another important thing is, how do you select the appropriate lubrication oil? Now, lubrication and oil selection is an important field, and that field is called as tribology. Tribology is study of friction wear and lubrication. And what you have is, you have something called as the coefficient of friction, and you have something called as the characteristics number, and that characteristics number depends upon uh, the contact pressure, the viscosity, and the speed, and then the coefficient of friction follows this type of profile. And the purpose, so if you think about n, which is the speed, p is the contact pressure, and z is associated with the viscosity of the oil. So what you want to do is, you want to select the oil that would maintain the operating region somewhere over here. You don't want coefficient of friction to be quite high, because that would increase the losses. You don't want coefficient of friction to be super high here, that will also increase the losses. So what's going to happen is, depending upon the speed at which the shaft is rotating, depending upon the contact pressure that we have, we choose the appropriate value of Z, and that is how the oil is selected. For example, if you go to some oil change service, Walmart, or maybe some lubrication or automobile shop, you want to get an oil change, there will be a specification 10 SA 10W5, SA 5W30. Those indicate the temperature stability and the viscosity of the oil, because you want to use the appropriate type of oil for the engine performance. Because think about it, what happens if the viscosity is too high? If the viscosity is too high, speed is constant, contact pressure is constant, what's going to happen is, you are going to go all the way over here, which would increase the coefficient of friction. So in other words, the viscosity would add a drag onto that components, that would increase the frictional losses. If the viscosity is too low, then the oil will not stick to the rotating surfaces, and coefficient of friction is going to be high. So you want to maintain the viscosity in particular range, so that the optimal power transmission can happen. The another thing that is important is the value of delta T. Delta T is the change in the temperature. And what happens is, as the temperature changes, the oil properties change. So viscosity drops down. So SA10W30 indicates that particular oil is stable over the specified, and when I say specified, to the specified by the SAE standards, specified over that temperature range. That's why many a times, if you use high performance car, they will ask you to use different types of oil in summer and different type of oil in winter. And the reason for that is because you want that engine to be in optimal performance, minimizing friction and maintaining appropriate heat transfer. So tribology is an interesting field, and I will talk more about the oil selection, friction, wear, and lubrication when we design gearboxes in next lectures. So here I am going to stop. We'll have a break of 15 minutes, and after we come back, I would like to work out one more spur gear design problem. from start to end, where we will do the wear load, we will do the dynamic load, and we will check the design, and then we will continue the discussion for the how do we use the same gear design technique for helical gears. So I'm going to stop here for 15 minutes, and after we come back, I'm going to work out a spur gear problem. Okay, now I'm going to solve the gear design problem, start to end. The problem goes something like this. Design a gear drive. Power transmitted 22.5 kilowatts. Velocity ratio is 1.2. RPM of pinion is 200. Approximate center distance. (600 millimeters). 20 degrees stub peak. And again it's involute. Sigma G is equal to sigma P is equal to 60 megapascal. Same material. For pinion and gear. B 10 times N. So first, find module face width. Number of teeth. And then last part, check for dynamic and wear load. So center distance is equal to RP plus RG. So module, number of teeth on pinion, module, number of teeth on gear divided by 2. So 1200 is equal to M times TP plus, as you know, the velocity ratio is 1.2. So TG divided by TP is equal to 1.2. So M 1.2 TP. So 1200 is equal to 1 plus 1.2 m times dp, and m times dp is dp. Where m is the module, number of teeth, female. So 2.2 dp. So we got dp is equal to 400 and so yeah, actually I got these, let me see, 1.2. Yeah, so actually my answers are incorrect. So just tell me what is the answer here? What is the value of dp? 5. And dg? What is the value of 2.2 times 545? Okay. So next step is we need to find out dp. So tell me what is this answer quickly. Six meters per second. Now 6 meters per second is less than 12.5 meters per second. So CV 3 plus V. So you get CV at 0.33. Lewis's form factor. Now please note minimum number of teeth to avoid interference is equal to 18. CS service factor, and I'm gonna assume 1. WT power V multiplied by service factor 22.5 10 to the power 3 divided by 6 multiplied by 1. Tell me what is this answer?
Basically, if there is no service factor mentioned, we assume it as
Correct. So since there is no service factor assumed mentioned, we assume service factor is equal to 1. Next, WT So tell me from here, what is the value of module?
well.
6.8. So we will say 7 millimeters. Now face width, or we can make it 8 millimeters, just 7 millimeters is fine. So dynamic load, WD, WT plus 21V P times C is WT plus square root of 3750. Now for value of C, please refer to the table. Yeah,
I need to read, and I'll send you an email.
okay, sure, that's fine. This lecture will be uploaded by tonight along with the slides. So C is equal to 8. And tell me what is the answer you get. Static load, sigma E the Kelvin value of WS.
I don't know, yes, 9,000.
9,000. So 9 kilonewton, right?
Hmm.
And what is WS?
Point 6 kilonewton.
So as you can see, WD, WS, safe.
What do you mean by dynamic load? Is it
So dynamic load is WT plus WI, which is intermittent load. So if you look at the gear is not statically loaded. So the gear loading is sort of the fluctuating load. So the gear is sort of loaded by fluctuating or alternating load. So dynamic load is the WT, which is the tangential load, plus a fraction of a tangential load that is assumed so that we can account for the fluctuating load or fatigue load. So that's why this dynamic load is considered. Next part is wear load. If you look at the wear load, it's always found for pinion, and Q is equal to 2 times velocity ratio divided by velocity ratio plus 1 as these are external gears. K is equal to sigma ES square sine phi so dp is the diameter of the pinion, which is 545. What is the value of q? 2 times 1.2 divided by 3, and the value of k. What is the value of k?
2.15.
And all said and done, what is this value? Wow, 67 kilonewtons. This is, so WD is less than WW. Your design is safe. And the next step is shaft design. You guys can do shaft design, or do you want me to work out the shaft design? Okay, we shaft design. Okay. Next step. Okay, so I'm going to quickly go through this problem, and then we will start the design of helical gears. Okay, this is a spur gear problem. In the spur gear design, the power is given to us 22.5 kilowatts. Velocity ratio is given to us. RPM of the pinion is given to us. And the approximate center distance is given to us. Now, please try to understand, center distance looks like a benign requirement, but it could be difficult to meet. So that's why what sometimes is done is you manufacture the gear or you purchase the gear and you basically grind the gear at the top. So essentially you make it a stub gear so that the center distance requirement can be appropriately met. For this particular gear, you have the same material, sigma G gear material, pinion material is 60 megapascals, and the face width B is 10 times the module. So that ratio is given to us, B is equal to 10 times M, and we have to find out the numerical value of module, face width, number of teeth, and check for dynamic and wear load. Hey, good, this problem does not ask for shaft design. Okay. So center distance is given to us. Center distance is the radius of the pinion plus radius of the gear, and based on that information, we can find out the diameter of the pinion. Then we can find out the diameter of the gear. Then we can find out the pitch line velocity, which is pi times d times n divided by 60. And that pitch line velocity is useful to find out the velocity factor CV. Once we have minimum number of teeth that are needed to avoid interference, which is 18, we can find out the value of the form factor YP. And then since the service factor is not given, I'm going to assume the service factor is equal to 1, and then I'm going to find out the value of the tangential load, which is the power transmitted divided by the pitch line velocity. And then use the equation WT is equal to CV times B times pi times M multiplied by the stress multiplied by the Lewis's form factor. And once we solve this equation, we land up with the module is equal to 7 millimeter. Since the ratio of module to face width is given to us, we can find out the value of face width, which is 70 millimeters. Once we know the face width, we have to find out the dynamic load. And I have to caution you at this point, okay? If you have not done this, I would ask you to pause for a minute, refer to the table in chapter 28 and find out the value of C. Because otherwise there are two places that value of C is given and you will get confused. So just for 1 minute, go to chapter 28 and look at the table where the tooth correction factor, error factors are given and the appropriate value of C is given. The material here is cast iron. So for that material, the value of C is 80. Then find out the dynamic load, which is 9 kilonewton. And I want you to notice this. The WT, which is the transmitted load or transmitted force, is about 3.75. But the dynamic load, which is because of the impinging or loading that is fluctuating, the dynamic load goes all the way to 9 kilonewton, about 2.2 times the static load. So next step is we need to find out if our gear is safe in this fluctuating load situation. So we go to table 28.8, find out the endurance strength of the material. And if you have not done this, again, I will ask you for a minute, go to table 28.8 and convince yourself that the value of sigma E is 84 Newton per millimeter square. Then find out the value of WS. And the value of WS is, as you can see, sigma E times B times pi times M multiplied by YP, and then you get 15.6 kilonewton as the static load. And since the static load is greater than dynamic load, the design is safe. The next part is we have to find out the wear load. To find the wear load, we have to first find out the value of Q. And this Q comes from whether the gear is internal or external. In this particular case, the gears are external. So value of Q is 0.8. We have to find out the value of K, which is the wear factor. And if you have not done it, just look and make sure that my equation is correct and you understand this process. So you have to go to table 28.9, use these values. Again, it's cast iron, so the Young's modulus is 90 gigapascals. I think I need to write this down. The material is cast iron. That's why the Young's modulus is 90 gigapascals, and that will get me the value of K. And then substitute all these values into the equation, and you are going to get the wear load of 67 kilonewton. And as you know, WD is less than WW. This gear design is safe. Everyone okay with this process? Okay. I'll just give you a 2 minutes break, a restroom break, and then I will start the spur, the helical gear design. Okay, so in the last part of today's lesson, we are going to talk about the helical gear. Now, first, let's understand the difference between the spur gear and the helical gear. So if you look at the spur gear, the gear teeth are parallel to the shaft. If you look at the spur gear teeth are parallel to the shaft. This is the spur gear. If you look at the helical gear, the gear teeth are cut at an angle. So in spur gear, you do not have axial force. Because if you look at the tangential force, it is like this. But in the case of helical gear, you get axial force. Helical gear are stronger. This is the helix angle. For helical gear, M also is called module, but B by M ratio is anywhere between 20 to 30 times module. The helix angle which is alpha, is typically 20 to 35 degrees. Now, the issue with the helical gear is because of the axial force. Usually in the helical gear, you add some type of a thrust bearing. Because once you have a helical gear, you are going to have the force parallel to the shaft, and that would slide the gear left or right. That's why you want to add a thrust bearing. So let's look at the nomenclature of the helical gear. What I'm going to show you, this is Pn, this Pc, Pc is axial pitch, Pn is normal pitch, and Pn is equal to Pc times the cosine of helix angle. Now, in order to overcome the issues with the axial force, sometimes what we do is we use double helical gear. So the issue with double helical gear is you are going to have an axial force from one helical gear. You are going to have an axial force from the other helical gear, and these two axial forces, they cancel each other. Now, in terms of design of helical gear, it's same as the design of spur gear. But only difference is we are going to convert a helical gear into an equivalent spur gear. So, and that is done using finding the equivalent number of teeth. So T is number of teeth on helical gear. PE is equivalent number of teeth on spur gear. And that equation is TE is equal to T divided by cosine cube alpha. So what does that mean? Take a helical gear, convert that into equivalent spur gear and design using spur gear principles. So that is how the gear design, the helical gear design is done. So let me give you some dimensions or the proportions for the helical gear. The pressure angle for helical gear is 15 to 25 degrees. Helix angle (20 to 45 degrees). Addendum 0.8 times module. Dedendum 1 times module. Minimum total depth is 1.8 times module. Thickness is equal to 1.5 times module. So these are the proportions of the helical gear. So what are the design steps? Step one, beam strength equation. So, and Y E is the Lewis's form factor based on equivalent number of teeth, TE. WT is equal to sigma naught times CV P pi M times Y prime. And this sigma naught comes from per gear design table. Or data book. The second part is the dynamic load. And the equations are similar, but I'll show you what the difference is. WD is equal to WT 21V C cosine square alpha plus WT cosine alpha, where alpha is the helix angle, divided by 21V plus and alpha, if you think about it, is 0 for spur gear. So if in this equation, you substitute alpha is equal to 0, you are gonna get the equation for the spur gear. Other than that, this equation is similar to the spur gear. Step 3, static tooth load. And static tooth load is Ws sigma E times B pi M times Y prime. And we need to make sure that WD is less than Ws. Last step is the wear load. And the equation for wear load K sigma ES square sine. The only difference here is we have to use sine Cn. So this Cn is called normal pressure angle. And we have to find out this normal pressure angle give from the equation. Okay, so the next part is the shaft design. So in helical gears, there is tangential load Wn, which is the normal load, Wr, which is the radial load, the axial load. So let me show you the helical gear, how it looks like. So if you look at the front view of the helical gear, if you look at the top view of the helical gear, so essentially you have 3D forces. And what I will do is, I will try to show you how these forces act on the helical gear. So what we have is, we have a tangential force First draw. Coordinate system. So we have this axial force here. We have this radial force over here. And then we have this tangential force over here. This is the normal stress, normal force. So this is how the three-dimensional state of stress or loading exists on the helical gear. So how would we solve this particular problem? So the first and foremost, we have to find out WT. WT is torque divided by the radius. And then what we have is we have this pressure angle, and then what we have is we have the helix angle. So this is the pressure angle, and this is the helix angle. So now you have the pressure angle and you have the helix angle that contribute to these state of stress. So what we do is then we find out the values of WT. From WT, we find out the value of WN. Then we find out the value of WR. Then we find out the value of WA. And follow the same process. We find out the bending moment in the horizontal direction. So BM in the horizontal direction. We find out the bending moment in the vertical direction. Then please understand, in this particular case, we have the torque. So we find out the total bending moment, Bm resultant is equal to square root of Bm in the horizontal direction, Bm in the vertical direction. Then we find the value of torque. And then we find TEQ divided by J multiplied by R and find out the value of diameter of the shaft. So the shaft design procedure is similar. The only thing is, compared to the spur gear, helical gear state of stress or the forces on the helical gear, they are more complicated. Now, what I want to do is, actually, I want to quickly solve a simple problem. Okay, I promise this is a simple problem, but let me quickly talk about the process. The process for the helical gear design is similar to the spur gear design. Step one is the beam strength equation. And again, we have to follow the same process as the spur gear. The only difference here is the ratio of B by M is different. B by M ratios are significantly larger for the spur gear because the width is much more than compared to the spur gear. We have to find out value of Y prime, which is the Lewis's form factor based on the equivalent number of teeth. Then we have to find out the value of the dynamic load. And the dynamic load is equation same as per gear, but now we need to take into account value of alpha. Then we have to find out the static tooth load, make sure that the dynamic load is less than static load. Then we have to find the wear load and make sure that the wear load is less than, the dynamic load is less than the wear load. W. So let's solve a simple problem. Design a helical gear. P is equal to 15 kilowatts, 20-degree stub, helix angle 45 degrees, speed of pinion is 10,000 RPM, diameter of the pinion is 80 millimeters, diameter of the gear is 320 millimeters. The material is cast steel. Sigma value is 100 Newton per millimeter square. We have to find out the value of B. We have to find out the value of module, and we have to check gear for wear. So first, power is equal to 2 pi nt divided by 60. Two times pi 10,000 t divided by 60. So torque is 14.3 Newton meter. Wt, which is the tangential load, is T divided by Rp, 14.3, 80,000 times M. Tp is equal to dP so Te So equivalent number of teeth, cosine cube alpha 80 cosine cube 45 226 and y prime So unfortunately, if you look at in this equation, everything is expressed in terms of module. So we have to start from the first step, and then at the end, module that's an unknown is going to float in every equation. Next step is the pitch line velocity, pi dn by 60 pi times 80 times 10,000 60 just a second. So we have to find out CV, and CV will be found out from the same set of equations that are given in Spur gear design. It's CV zero 0.75 into 0.1. Now I'm just going to assume, so B is equal to 12.5 m WT sigma naught CV times B times pi times m y prime. When you solve this, module is going to be 3 millimeters and B will be 12.3 times module. Next step. So please note, in this problem, they are not asking us to find out to check for the static stress. So I'm going to skip step number 2 and go to the checking for wear, because that is what is asked. Check gear for wear. And when I say gear, you always must check pinion. So velocity ratio is equal to 4. It's an external gear. Is equal to Q 2 times 4, 4 plus 1, 1.6. At this point, we have to find Vn, the normal pressure angle. Equation is tan Vn tan phi cosine alpha. Tan 20 cosine 45 Vn is equal to 14.4. EP is equal to EG is equal to 200 Newton per millimeter square. 200 multiplied by 10 to the power 3 Newton per millimeter square because it's steel. So when you use the equation, K is equal to sigma ES square sine Vn divided by 1.4, 1 divided by EP plus 1 divided by EG. This answer is 0.675 Newton per millimeter square. Now the last part is we have to find out WW, DP, B, Q, K, 5554 Newton. This is greater than WD. So design is safe. And this is actually a very simple problem to demonstrate the approach. But I'm going to work out one more problem wherein we will actually go through the whole process and design the shafts. So just to quickly give you background on the helical gear. Helical gear design is similar to spur gear. But the only difference is we had to find out the equivalent number of teeth. Then if you look at this design, in this problem, we have to design a helical gear, and it's, to be honest with you, the helical gear is pretty much designed. The only thing what we need to do is find out the value of B, find out the value of module, and just check the gear for wear. So what we want to do is we want to find out the value of P, then we need to find out the value of B, then we have to find out the value of the phi n, and finally we want to find out the value of WW. And then since WW, we show that it is greater than WD, the design is safe. And just for the sake of completion, I just want to find out WW and WD. So dynamic load WD, WT 21V, PC cosine square alpha, WT cosine alpha divided by 21V plus square root of PC cosine square alpha plus WT. So you will want to find, and again, the value of C will come from chapter 28 and alpha value is 45 degrees, and then you need to just check that this design is safe. So this is a very simple problem, but what I'm going to do is the next class I would actually work out a slightly more involved problem. And then we will actually work out. I don't have time to finish this problem. The next class, I will actually work out this problem. And then we will proceed on to design of bevel gears. So once we are done with bevel gear design, the last gear that we want to design is the worm wheel. And after worm wheel is designed, we'll move on to the design of internal combustion engines. So wherein we would design the piston, cylinder, connecting rod, crankshaft, and then try to look at how that engine is put together. I will bring some engine models to the class. That way you will be, you'll actually see how the piston looks like, connecting rod looks like, and how the whole thing is assembled, and what are the important components of an internal combustion engine, because internal combustion engines are ubiquitous. So they are used almost everywhere. With that, I'm going to stop here today, but I would be happy to